Good morning. This is Hope Reactor. Now, let's begin today's news.
Why don't giant trees take over the forest? A giant tree reaches high above the forest. Its leaves capture the sunlight first, while the smaller trees below are left in shadow. So why do the small trees not disappear? At first glance, a forest looks peaceful. The wind moves gently through the leaves. Birds call from somewhere in the distance. Sunlight falls between the branches. But above the forest floor, a fierce competition is taking place. Trees need sunlight to produce energy. Because sunlight comes from above, taller trees have a powerful advantage. They can spread their leaves over smaller trees, capture the light first and cast shadows below. The competition is not equal. A short tree cannot cast a shadow upward and block a taller tree. This means that forest competition often favors the trees that reach the canopy first. If that advantage continued forever, an old forest should contain only a small number of enormous winners. But that is not what we see. In mature forests that have existed for more than a century, giant trees live beside medium-sized trees and small trees. Different species, different heights, and different survival strategies all remain in the same forest. Why does the winner not take everything? A research team led by Kyoto University found an important answer. The scientists studied 12 forest plots at the Tomakomai experimental forest in Hokkaido, Japan. These forests ranged from areas recovering for only 16 years. After major disturbance to forests more than 100 years old, the researchers measured the three-dimensional distribution of light inside the forest. They used small light sensors attached to an extendable 20-meter carbon pole. They also mapped the three-dimensional shapes of individual tree crowns and estimated how much light each tree received. In total, the research included more than 2,000 trees from 50 different species. The team then separated tree growth into two different abilities. The first was light interception efficiency. This means how much sunlight a tree can capture, compared with the amount of trunk, branches, and leaves it has built. The second was light use efficiency. This means how effectively the tree can turn the captured sunlight into new biological growth. In simple terms, one ability is about getting light. The other is about using light. These abilities may sound similar, but the study showed that they create a powerful trade-off. Tall trees were better at capturing sunlight. Their leaves were placed high in the canopy where light was abundant. But tall trees were less efficient at converting that captured light into further growth. Large trees must maintain thick trunks, extensive roots, and long water transport systems. Their upper leaves may also receive more sunlight than they can fully use. The giant tree wins the battle for light, but maintaining its enormous body is expensive. Small trees face the opposite situation. They receive far less sunlight, but many shade-tolerant species are highly efficient at using the little light that reaches them. They cannot compete with giant trees in quantity. Instead, they survive through efficiency. This difference becomes especially important as a forest grows older. In a young forest, the race is fast and unforgiving. The trees are still filling open space. A tree that becomes slightly taller can capture much more sunlight than its neighbors. That extra light helps it grow even faster. A small difference in height quickly becomes a large difference. The winners rise. The slower trees fall deeper into shadow. Some eventually die. This stage creates the dramatic height differences seen during forest development. But in a mature forest, the rules begin to change. The canopy is already high and crowded. Even tall trees no longer gain the same overwhelming advantage from becoming slightly taller. At the same time, shade-tolerant species establish themselves below. These smaller trees may capture little light, but they convert it into growth with remarkable efficiency. As a result, giant trees and small trees can achieve similar growth rates relative to their own size. The large trees remain powerful light collectors. The small trees become careful light users. They share the same forest, not because competition has disappeared, but because success no longer depends on only one ability. This discovery changes the way we understand coexistence in nature. A mature forest is not peaceful because every tree receives an equal share. It is stable because different trees succeed in different ways. One tree survives by reaching the sun. Another survives by making the most of the shadows. Competition creates growth, but differences in efficiency create coexistence. This research may also help improve forest management and climate models. Forests store carbon, protect water, provide timber, and support countless forms of life. But managing a forest only for rapid growth may reduce the variety of tree sizes and species. Protecting every forest without active management may also create problems, especially in plantations that require thinning and renewal. The better choice depends on the purpose of the forest. Some forests may be managed for timber production. Others may be protected for biodiversity, carbon storage, water conservation, or resilience. By measuring forest structure and light more precisely, researchers and forest managers may eventually make better decisions about which trees to retain, where to create space, and when intervention is necessary. One major question remains: will this balance between giant trees and small trees survive under climate change? Higher temperatures, droughts, storms, and changing rainfall could alter the amount of light and water available inside forests. Large trees may struggle to transport water through their tall bodies. Small shade-tolerant trees may also face conditions they have never experienced before. The researchers are now applying the same approach to forests in other climate zones, including warm temperate and tropical regions, to test whether this principle works across the world. The forest leaves us with a powerful lesson. Growth is not always about taking the most. Sometimes survival depends on using limited resources better than anyone else. The giant tree and the small tree do not possess the same strengths. That difference is exactly what allows both to remain. The next time you walk through a forest, look beyond the tallest tree. Notice the young trees waiting beneath it. Even in the deepest shadow, life is quietly turning a small amount of light into a future. What looks like a silent forest is actually a living system of competition, adaptation, and coexistence. What we do not know can become hope. This is Hope Reactor.